Hello everyone! Have you ever wondered how scientists measure things that are incredibly small? I'm talking about nanoparticles, polymers, or even proteins in a solution, things far too tiny to see with a standard microscope. Today, we are going to explore a powerful technique that lets us do just that. We're talking about static light scattering. At its heart, static light scattering, or SLS, is surprisingly straightforward. Imagine shining a flashlight into a dark, dusty room. You don't see the individual dust particles, but you see the light they scatter. SLS works on the same principle. We shine a very stable and focused beam of light, usually from a laser, into a liquid sample containing our tiny particles. When this light hits a particle, it gets scattered in all directions. A sensitive detector then measures the intensity, or brightness, of this scattered light. The key word here is static. We aren't looking at rapid fluctuations, we're measuring the average intensity of the scattered light over a short period of time. So, what does this tell us? First and foremost, SLS is fantastic for determining the molar mass, which is directly related to the size of the particles. The fundamental rule is simple: bigger particles scatter more light. So, by measuring how bright the scattered light is, we can calculate the average molar mass of the particles in our sample. This is incredibly useful for characterizing everything from new drug delivery nanoparticles to long polymer chains. But SLS can tell us even more. By placing the detector at different angles relative to the initial laser beam, we can learn about the particle's shape. Think about it: a long, rod-like particle will scatter light differently than a compact, spherical one. This angular dependence of the scattering intensity allows us to calculate something called the radius of gyration, or RG. The RG gives us a measure of the particle's overall size and how its mass is distributed, offering clues about its shape and structure. Furthermore, by performing measurements on samples at different concentrations, SLS can reveal how the particles interact with each other and with the liquid they're dissolved in. This information is captured in a value called the second virial coefficient. A positive value suggests the particles prefer to be surrounded by the solvent and tend to repel each other, which is good for stability. A negative value indicates that the particles attract each other, which might lead to clumping or aggregation. In essence, SLS doesn't just measure particles in isolation, it tells us about their social behavior in a solution. So, to quickly recap, static light scattering is a non-invasive technique that uses a laser to measure the time-averaged intensity of scattered light to determine the molar mass, the radius of gyration, and the interaction behavior of particles in a solution. It's a cornerstone technique in many fields of science and engineering. Thank you so much for watching and learning with me today. If you found this video helpful and want to see more explanations of scientific concepts, please consider giving it a thumbs up and subscribing to support the channel. Your support allows us to keep making this content. We'll see you in the next video.